Hi, and welcome to Thermodynamics for Educators Week 9 Mini Lecture 1. In this lecture, I'm going to discuss how to think about the various thermodynamic potentials that you'll be introduced this week and attempt to give you some sort of intuitive feel for what they mean, building on what you'll be reading this week in the textbook and the other journal articles. So the four most common thermodynamic potentials are the internal energy, the Helmholtz free energy, the enthalpy, and the Gibbs free energy. And to remember how to get from one to the other, you can organize them in this square here. This is also reproduced in the book. If you start from the internal energy, then moving to the right means you subtract temperature times entropy, and moving down means you add pressure times volume. The internal energy is just the energy of the system. The enthalpy is the energy needed to create that system, so it's internal energy, plus the work needed to make room for it. The Helmholtz free energy is the energy needed to create the system, minus the energy that you can get from the environment. And the Gibbs free energy is the total energy needed to create a system and make room for it, minus the energy you can get from the environment. Now, before we move on, I just also want to point out that the Helmholtz free energy is most commonly denoted by the letter F, but you will also see it referred to as A. I think in at least one of the articles you'll be reading this week, the Helmholtz free energy is called A. Okay, so let's try and picture what these thermodynamic potentials mean. So in general, we have a thermodynamic system that we're interested in, and it is interacting with the surroundings. Okay, now I'm going to divide the surroundings up into a general part, which I'm going to call the surroundings, and a small part that I'm going to call U. The thing that I'm labeling U is the active part of the surroundings. It's the part of the surroundings that actively does work on the system, or the system does work on. The surroundings themselves, the inactive surroundings, are just everything else that just sits there and can exchange heat with the system. Now, the system has some internal energy U. This is the energy of the system. And when the system gets created, you need to provide this energy U. But also the system has to push a volume V of the surroundings out of the way to make room for itself. So we need to supply an amount of work PV as well as the internal energy U required to create the system. Now, some of the energy that we provide to create the system can come from the surroundings that are just sitting there around the system. They provide some amount of heat, T times S, into the system. Okay, this heat is just heat that naturally flows into the system when it appears there, when it gets created. And that can provide some of the energy required to create the system. Now, in order to create the system and make room for itself, you and the surroundings need to provide the internal energy plus the work done to make room for the system, U plus PV. So this is the total energy you and the surroundings must provide, and that's what we call the enthalpy. But the surroundings that are just sat there already provide an amount of heat, Ts. So that's part of the necessary energy required to create the system and move the surroundings out of the way. So it's often more relevant to talk about the amount of energy that you need to provide. In other words, the amount of work that you need to put in to create the system, not just the amount of heat that flows into the system from the surroundings. So in order to calculate that, you just take the total energy that you and the surroundings provide, and you subtract the energy that the surroundings provide. And that leaves you with the total energy that you have to provide. And that is the Gibbs free energy. So that is essentially the energy. So that is the energy you need to provide that isn't already provided by the rest of the surroundings in the form of heat flowing into the system. Now, if the system is created at constant pressure, then that means you definitely have to move some of the surroundings out of the way. However, if we're interested in changes to the system at constant volume, and so there's no extra work having to be done on the surroundings, then the Helmholtz free energy is the more useful quantity. So this is the energy that you need to provide, excluding the energy needed to make room for the system. So in other words, it's just you need to provide an internal energy, and then you subtract off the energy provided by the surroundings. Okay, now let's talk about changes in the thermodynamic potentials. So it's changes in the potentials that are the things that you're going to deal with most often. And from the thermodynamic identity for internal energy, you can derive the thermodynamic identities for the other three thermodynamic potentials. It's useful to remember that each term in a thermodynamic identity contains a pair of variables, and one of the pair is intensive and one of the pair is extensive. In other words, one of the pair doesn't change when you double the size of the system, and one of the pair doubles in size when you double the system. So temperature and entropy are one pair, Entropy is intensive, temperature is extensive, and pressure and volume are another pair. Volume is intensive, pressure is extensive. And the thermodynamic identity for internal energy we're familiar with by now is just TdS minus PdV. Okay, so the form of the identity tells you under what circumstances the identity is useful. This is useful when we're dealing with changes in the internal energy due to changes in entropy and volume. So pressure and temperature are constant. The thermodynamic identity for enthalpy is dH is TdS plus VdP, so we've switched which one of this pair of variables is changing from volume to pressure. Alternatively, we could keep volume as the variable that is changing, and we could swap around the other pair. So we could change TdS to minus SdT. Notice that when you swap a pair of variables around, you add a minus sign in. That gets you the thermodynamic identity for the Helmholtz free energy. And finally, for the Gibbs free energy, we swap both T and S and P and V around in the first relation to get minus SdT plus VdP. Now, the variables that are changing, these tell you what the independent variables are when you use that particular relation. So if you're using this thermodynamic identity in a problem, then the independent variables are S and V. For enthalpy, the independent variables are S and P, and so on. T and P will themselves be functions of S and V. So once you determine S and V, you can determine temperature and pressure and so on via an equation of state. Now, to figure out when it's useful to use any of these relations, let's recall some things that we already know. So this term TdS here is the heat flow into or out of a system. In the first thermodynamic identity here, the one for internal energy, it is the heat into the system at constant volume, CV dt. Whereas for the enthalpy relation, it's the heat in at constant pressure, Cp dt. So if you're interested in heat into or out of a system under conditions of constant volume or constant pressure, then these two relations are the ones to use. Let's turn our attention to work done. So for the thermodynamic identity for internal energy, minus PdV is the work done by the gas during an adiabatic quasi-static process. So in other words, the change in entropy is zero. Whereas for the Helmholtz free energy, it's the work done by a gas during an isothermal process, one where dt is zero. So you know that if you're interested in work done, if it's an adiabatic process, you're going to use the internal energy identity. If it's an isothermal process, it's most useful to use the Helmholtz free energy. I'll come to a couple of examples which show us when it's useful to use the Gibbs free energy in a minute. And finally, the maximum total work a system can do during any process is just equal to the change in the Helmholtz free energy between the starting and ending points of that process. And additionally, for processes where temperature and volume are constant, the Helmholtz free energy decreases to a minimum as the system goes towards equilibrium as the entropy increases to a maximum. This relation here holds for equilibrium states. So at temperature and volume constant, dF is zero, and you've reached a minimum in the free energy. So at constant temperature and volume, a system is going to try and minimize its Helmholtz free energy. The change in the Gibbs free energy between the start and end points of any process is equal to the maximum non-expansion work a system can do during any process. And for processes where temperature and pressure are constant, it's the Gibbs free energy that decreases to a minimum as entropy increases to a maximum as the system tries to find equilibrium. Now let me briefly mention that, of course, there are two other variables that we have been introduced to that form a part of these thermodynamic identities. They are chemical potential and particle number here. In all of these identities, the third term is mu dn. You can, however, swap these two variables around to create a term n d mu. And if you do that, you'll create 4 more thermodynamic potentials to bring the total to 8. We're not going to need to know this for this course, but one can take the thermodynamic potential square that I showed at the start of this lecture and make it into a cube if you want to remember all 8 thermodynamic potentials. The additional 8 here are given by these additional symbols here. So let me go over a couple of examples. Firstly, this is the example that was covered in the textbook concerning the electrolysis of water. So I just want to go through it on our little picture of the system versus the surroundings. So in the electrolysis of water, we are causing this chemical reaction to happen, H2O, the decomposition of water. The decomposition of water, H2O, goes to H2 plus a half O2. So that's the thing that we're causing to happen. And if we look up the enthalpies of each of the reactants and products, then this chemical reaction is associated with a change of 286 kilojoules. So that's the amount of energy that needs to be provided to the system for this reaction to occur. Who's providing it? Well, the surroundings and yourself. Okay, now where is this energy going to? Well, one of the products is a gas, and that gas has to expand into the surroundings if we are conducting this experiment at constant pressure, which we usually are. And that takes an amount of work of 4 kilojoules. So 4 kilojoules of this 286 goes into making room for the oxygen gas, and that means that the rest must go into changing the internal energy of the system, which must increase by 282 kilojoules. Now, if you look at the change in entropy in this reaction, then you'll find if this is being conducted at room temperature, that an amount of heat of 49 kilojoules has to be provided into the reaction. So that's 49 kilojoules out of the 286, and that means that you have to provide the other 237 kilojoules in the form of work of some kind. And in this case, it's electrolysis, so we're providing electrical work here, as denoted by this spark coming out of your fingers. Okay, let me go through problem 5.5, which deals with a methane fuel cell, or natural gas fuel cell, which is depicted schematically here. So in this, we are causing the reaction CH4 plus 2O2 goes to 2H2O plus CO2. So this is oxidation of methane, not by combustion, but by providing electrical work. So here we're oxidizing methane in order to provide electrical work. So if you look up the enthalpy values of the reactants and products, you can compute the change in enthalpy, and you'll find it's minus 891 kilojoules. So that enthalpy is coming out from the fuel cell into the surroundings, plus yourself. Do the same calculation for the Gibbs free energy, and you get minus 798 kilojoules. So that's the amount that you get that isn't heat given up to the surroundings. So in other words, that's the amount of electrical work that you are going to get out, 798 kilojoules. The difference between these two must be the amount of heat that exits the system. So that's the amount of heat into the surroundings, that's 93 kilojoules. So that's how the energies break down for this reaction. You can see from this diagram that the reaction causes 8 electrons to be moved from the cathode to the anode every time this reaction happens. That means in 1 mole of reactants, you're going to get 8 electrons times the number of molecules in a mole times the charge of an electron, which gives you 7.7 times 10 to the 5 coulombs of charge that gets moved from the cathode to the anode. You can then calculate the voltage of this fuel cell. It's simply the energy that you get out when 1 mole of the reactants changes into a mole of the products. That's what we calculated, 798 kilojoules. That's the amount of electrical work we get out. And if you divide that by the charge that is moved as a result of this work, then you get the voltage, which comes out to about 1 volt. Finally, let me go through problem 5.10, raising the temperature of water. So let's suppose we want to raise the temperature of a tub of water from 25 degrees Celsius to 30 degrees Celsius. So the change in the Gibbs free energy in this case is given by the thermodynamic identity. We're doing it at constant pressure, and we're not going to lose any molecules of water, so the Gibbs free energy change is minus SdT. Entropy of water is about 70 joules per kilogram. We're raising the temperature of water by 5 Kelvin, so the change in the Gibbs free energy is about minus 350 joules. So Gibbs free energy drops. We're getting Gibbs free energy out into the surroundings in this process. But hang on, weren't we just adding heat into the system? So what's happening here? Well, let's calculate how much heat we had to put into the water in order to raise its temperature by 5 degrees C. We're at constant pressure, so that's just Cp delta T, and this is going to be the change in internal energy in the water. Look up the heat capacity at constant pressure and plug it in, and you get that we're having to put about 377 joules of heat into the water to raise its temperature by 5 degrees, assuming that we've got a mole of water here. So the change in internal energy is about 377 joules, but we're additionally getting about 350 joules of Gibbs energy that comes out into the surroundings. So the amount of energy that we're having to, the amount of heat that we're having to put in is actually the sum of these two things. It's actually 726 joules we're putting in to this tub of water, and only about half of it is going into raising the temperature of the water. The rest of it is being lost into the surroundings. So how can you heat the water without giving up any other energy into the surroundings? Because this seems very inefficient. Well, one way, by looking at the thermodynamic identity here, is to change the pressure of the water, to increase the pressure of the water in such a way that VdP balances minus SdT. And then delta G is 0, and we lose no Gibbs free energy into the surroundings. So we could imagine doing work on the water in order to increase the pressure as it is being heated up. So how much pressure do we have to exert on the water in that case? Well, this term here, V delta P, has to be equal to plus 349.5 joules to compensate for the minus 349.5 joules that we lose due to the change in temperature. We can rearrange this. We just divide 350 by the volume of a mole of water, which is 18 cubic centimeters, and we get about 2 times 10 to the 7 pascals, which is about 200 atmospheres. So we actually have to put a huge pressure on this water in order that it heats up without giving up heat into its surroundings. If we do that, then what happens now is that the amount of heat that we provide is only 376 joules. And that goes into changing the temperature by 5 degrees. But we're also doing 350 joules of work on the water, and that causes the internal energy of the water to increase by about 726 joules.